Welcome to This Explainer. Today, we're diving straight into a massive and, frankly, super fascinating engineering challenge. How exactly do you measure the fuel economy of industrial machines when they operate in vastly different ways? I mean, it sounds like a simple enough question, right? But the deeper you look into it, the more complex it actually gets.
Think about it for a second. The standard miles per gallon metric that we all use for our personal cars, it completely fails in the industrial world. It makes literally zero sense when you're dealing with, say, a 40-ton excavator that spends its entire day just sitting in one spot digging a hole, or a stationary generator that simply runs in place to provide utility power. If a machine isn't actually traveling a distance, how do we track its efficiency?
So here is our roadmap to demystify this whole thing. First, we'll look at the fuel efficiency challenge overall. Then we'll break down on-road heavy-duty vehicles, non-road construction equipment, and stationary power generators. And finally, we'll wrap up by measuring the bigger picture.
Let's start with part 1, the fuel efficiency challenge.
To really get this, just picture a massive semi-truck hauling freight, an excavator moving earth, and a generator producing power. You instantly realize they perform entirely different tasks, right? So logically, each one requires a distinct unit of measure that reflects its unique operational reality. We really just need the right tool for the job.
And if you check out the official SASB standard documentation for industrial machinery and goods, you'll actually see this elegant solution in action. Grouping these efficiency metrics by their operating context is a formalized requirement under their fuel economy and emissions use phase topic. Getting this right is absolutely critical if we want accurate, comparable environmental reporting across the entire industry.
Moving on to part 2, on-road heavy-duty vehicles. Before we get into the math, we really need to define our scope here. This specific standard, known as Metric RT-IG 410A.1, applies to medium and heavy-duty vehicles. We're talking about commercial combination tractors, semi-trucks, heavy-duty pickup trucks, and vocational vehicles. The key threshold to remember here is weight. To fall into this category, the vehicle has to weigh a minimum of 3.5 metric tons, which is right around 8,500 pounds. So how do we actually measure their efficiency? Well, for these massive beasts, manufacturers use liters per 100 tonne-kilometres, and this is key. They aren't just measuring the distance the truck traveled. They're accurately measuring the fuel efficiency of moving massive amounts of weight over that distance. It calculates the actual work of moving mass, which, as you can guess, is a far more accurate reflection of a freight truck's true efficiency than just a basic miles per gallon rating. Which brings us to part 3, non-road construction equipment. Now, because these machines, like excavators, agricultural tractors, and heavy forklifts, perform stationary heavy labor instead of cruising long distances down a highway, using kilometers or miles is pretty much useless. Instead, for metric RTIG 410A.2, their efficiency is logically measured strictly in time. We're looking at liters of fuel consumed per hour of operation. To report this metric accurately, engineers actually have a strict hierarchy to follow. First off, they should use the available manufacturer-rated fuel efficiency for that specific piece of equipment. But hey, if that model-rated value is unavailable, they can't just guess. They are required to calculate the operational efficiency by assuming normal, reasonable conditions for the load factor, the speed, and the environmental conditions. It's really all about finding the most grounded, realistic number possible. Next up, part 4, stationary power generators. Here, for metric RTIG 410.3, the machine's entire purpose isn't movement or mechanical labor. The output is pure energy. So the metric shifts again, this time to kilojoules per liter. Now, to figure out the sales-weighted fuel efficiency for a whole fleet of these stationary machines, manufacturers don't just add them all up and divide by the total. Oh no, they are required to use a clever mathematical concept called the harmonic mean. Okay, I know breaking down math formulas can be a bit daunting, but stick with me, because this is actually brilliant. Step 1, you start with the design fuel efficiency in kilojoules per liter. Step 2, you calculate the reciprocal of those values and average those reciprocals. Step 3, you find the reciprocal of that average. Now, this isn't just complex math for the fun of it. Using the harmonic mean is absolutely vital because it ensures we accurately capture the average amount of fuel needed by each generator to produce a given amount of power. If you just used a simple arithmetic mean, highly inefficient outliers would totally skew the overall data. The harmonic mean gives us the true, unskewed picture of the fleet's performance. Finally, part 5, measuring the bigger picture. So, zooming out from all those granular engineering calculations for a second, why do these distinct SASB metrics matter so much for the industrial machinery sector? Well, it's worth noting these standards are under the stewardship of the IFRS Foundation. Machinery manufacturers use massive amounts of raw materials, and more importantly, they produce products that release significant greenhouse gases and emissions during their use phase. Because these machines are deployed all over the world, having accurate, standardized apples-to-apples reporting is critical for investors and regulators globally to actually understand a company's true environmental footprint. And for the manufacturers themselves, this is absolutely not just a box-checking compliance exercise. Mastering these specific categorical metrics allows companies to proactively manage their climate-related risks. By developing products that excel in these specific use phase metrics, manufacturers can meet the rapidly growing customer demand for energy efficiency. They can capture expanding market share, stay ahead of increasingly strict jurisdictional regulations, and ultimately boost their overall brand value. It's basically a competitive advantage disguised as a reporting requirement.
Which leaves us with a really fascinating question to ponder as we wrap up. We've just explored a highly precise system built largely around measuring the consumption of liquid fossil fuels. But as this sector increasingly transitions to electric batteries, hydrogen cells, and other renewable energy sources, how are these foundational efficiency metrics going to need to evolve next? It's a massive challenge on the horizon for industrial manufacturing, engineering innovation, and sustainability reporting. Thanks for joining me for this explainer, and keep exploring.